Hi all, I am Shijo JS. This is the previous question paper discussion section of the subject Mechanics of Solids. In this section, we are going to discuss the previous question paper of the subject Mechanics of Solid in chapter wise. These are the chapter we are going to discuss. First one, stresses and strain. Second one, elastic constants. Third one, Morse circle. Fourth one, thin cylinders. Fifth one, shear force and bending moment diagrams. Sixth one, bending of beams. 7, torsion of shafts. 8, springs. 9, Euler's theory. And 10, strain energy. Chapter 1, stresses and strain. First question, in a cylindrical elastic body subjected to pure torsion, here body is subjected to pure torsion, about its axis develops. Option A, tensile stress in a direction 45 degree to the axis. Option B, no tensile or compressive stress. Option C, maximum shear stress along the axis of shaft. D, maximum shear stress at 45 degree to the axis. And here a cylinder, and a cylinder is subjected to a pure torsion. And this is a cylinder and it is subjected to a pure torsion. I am considering a small element here, small element, and this is the enlarged view of that small cylinder, a small element, and this is the shear stress too. Then first option, tensile stress in a direction 45 degree. In this case, I am considering a 45 degree plane. This is a 45 degree plane. In this plane, a normal tensile stress is acting. But in this question, there is nothing about the direction of torque applied. If the direction of torque applied is, if I am reversing the direction of torque applied, then the stresses are also reversed. This is the stresses. In this case, if I am considering a 45 degree plane and this is the axis of the shaft, 45 degree plane, in this case, compressive stress is acting along the 45 degree plane. So, we cannot say that there is always tensile stress in a 45 degree plane. This is also a 45 degree plane, 45 degree to the axis of the shaft. In this plane, compressive stress is acting. So, we cannot say that there is always tensile stress in a direction 45 degree. In some cases, there is tensile stress. In some other cases, compressive stresses are there. Option B, non-tensile or compressive stress. This option is wrong because there is tensile or compressive stress is acting. Then maximum shear stress along the axis of the shaft. This is the axis of the shaft. This is the axis of the shaft, and this is one of the maximum shear stress plane, and this is the another maximum shear stress plane. Here we can see that one pair of maximum shear stress plane is parallel to the axis and other shear stress plane is perpendicular to the axis. And option C is also partially correct. Then maximum shear stress at a 45 degree to the axis. That is wrong because this option is wrong because maximum shear stress is not acting at a 45 degree plane. It is acting at this plane and this plane. So we can option B and option D are wrong, but option A and option C are partially correct. But there is no exact answer, but the given option is option A, tensile stress in direction 45 degree to the axis, but it is not always true. In some case there is compressive stress is also there. Then 1.2, the three-dimensional state of stress at a point is given by, there is a matrix is given, then shear stress on x phase in y direction. We need to find out shear stress on x phase in y direction. So these are planes x, y, z. These x, y, z are planes, and these x, y, z are direction. These are direction, and these are planes. So we need to find out shear stress on x face. This is the x face in y direction. This is the y direction. So 10. Option C is the correct answer. Option C. 10 meganewton per meter square. That is the correct answer. Shear stress acting at x face in y direction. Then 1.3. A large uniform plate containing a rivet hole is subjected to uniform axial tension of 95 megapascal. This is stress value. Stress value is equal to 95 megapascal. The maximum stress developed in this plane. So we need to find out the maximum stress developed. The maximum stress developed is equal to sigma max is equal to load should be maximum, max by area should be minimum. Load by area is equal to stress. Stress is equal to maximum load by minimum area. In this case, the load is constant, and the load acting, maximum load P acting is stress into area. Load acting is equal to P is equal to stress into area. Stress is 95 into area. I am considering the area. Let T be the thickness of the plate. And this is T, and this height is 100 mm. So stress into area, force acting at two ends, stress into area, 95 into area is equal to 100 into T. This is the load acting. Then minimum area. Here load acting is constant, but area of cross section is not constant. We need to consider minimum cross sectional area. Here the minimum cross sectional area, there is a rivet hole, and this is the minimum cross sectional area. This hashed is the minimum cross sectional area. A mini is equal to minimum cross sectional area is equal to this height 100 into 100 minus 50. There is a rivet hole, 100 minus 50. Area is equal to 100 minus 50. There is a hole is there into thickness T. This is the minimum area. Therefore, maximum stress is equal to, this is the area mini. Maximum stress is equal to load by minimum area. Here load is equal to 95 into 100 into T, and minimum area is equal to 50 into T. T can be cancelled. This is 2. 2 into 95 is equal to 190 megapascal. Therefore 190 megapascal. Option C is the correct answer. 190 megapascal. Question number 1.4. Below figure shows a rigid bar hinged at A and B, supported in horizontal position by two vertical identical steel wires. Neglecting the weight of the beam, the tension T1 and T2 induced in these wires by a vertical load P applied as shown are. Here we need to find out the tension acting on string. Here we need to find out the tension acting on string T1 and T2. Here there are two unknowns, T1 and T2. We need to find out two equations to find out this unknown. So two equations are required. Generally equations are found out by using equilibrium condition, sum of forces is equal to 0 and sum of moment about any point is equal to 0. Here we cannot use sum of forces is equal to 0 because there is no force along horizontal direction, we cannot use sum of forces along horizontal direction is equal to 0. But if we are using sum of forces along vertical direction is equal to 0, it will add one more reaction here, RA. We need to consider one more reaction. So we cannot use the sum of forces along vertical direction is equal to 0, but we can use sum of moment of forces about any point. Here point A is equal to 0. We are taking A because if we are taking moment about A, the reaction moment due to this reaction will be 0. The sum of moment about A is equal to 0. We can take clockwise or clockwise moment as positive or counterclockwise moment as positive. We can write, I am taking moment of forces about A. First force T1, this is clockwise, I am taking clockwise as positive. Force into T1 into perpendicular distance is A, T1 into A. Then second force T2, T2 into B, that is also clockwise direction, plus T2 into B. Then there is a load P is there, and this is counterclockwise moment, which is minus P into L is equal to 0. So we can write T1A plus T2B is equal to P into L. This is the equation number 1. Now we need to find out one more equation. That equation can be found out by using the deflection of these strings. Deflection of string. This is a question given. Due to the point load P applied, this is the deformation of this bar. This is the deformation. And this is angle theta. And this is angle theta. Let delta 1, this is delta 1. Delta 1 is the deflection of string or elongation of string number 1. And this is delta 2. Delta 2 is the elongation of string number 2. And I am considering triangle. This is A. I am considering this as point B. And this is point C. Triangle ABC. In triangle ABC, tan theta is equal to opposite side. Opposite side is delta 1 by adjacent side. Adjacent side is A. In triangle, I am considering another triangle A, B, C, A, D. This point is D and this point is E. A, D, E. Triangle A, D, E. In triangle A, D, E, tan theta is equal to opposite side delta 2, opposite side by adjacent side. Adjacent side is B. Here the angle theta is same. So tan theta is also same. So we can equate these two equations. We get delta 1 by A is equal to delta 2 by B. Delta 1 is the elongation of string number 1 and delta 2 be the elongation of string number 2. We have elongation delta 1 is equal to PL by AE. P is applied load, L is length, A is area of cross section and E is Young's modulus. We have equation to find out elongation delta is equal to PL by AE. PL by AE. Here P, load acting on string number 1 is T1. L is L. Area of cross section A, Young's modulus is E. They are made of same material. Similarly, delta 2 is equal to T2L by AE. T2L by E. Here the length of two strings are same, area of cross section of string is same, and they are made of same materials also. Therefore, Young's modulus is also same. Substituting this value in equation, this equation delta 1 by A is equal to delta 2 by A, we get LAE will be cancelled. We can write T1A is equal to T2B. From this I can write T1 is equal to A by B into T2. T1 is equal to A by B into T2. Substituting this value in equation number 1, we have equation number 1 T1A plus T1A, equation number 1 plus T2B is equal to P into L. This is equation number 1. Substituting the value of T1 is equal to A by B into T2. We can write T1 is equal to A by B into T2 plus T2 into B is equal to P into L. I am multiplying this equation 2 into A by B into T1 into A plus T2 into B is equal to P into L. And multiplying this equation by B, we get A square T2 plus B square T2 is equal to P into B into L. From that we can, common factor is there, T2 into Ax square plus B square is equal to PBL. From this T2 is equal to PBL by A square plus B square. PBL, T2, PBL, T2, PBL, A square plus B square. PBL, only one option is here, option B. T2 is equal to PBL by A square plus B square. Therefore, the correct option is B. Similarly, you can find out T1 also, and the correct option is option number B. Then 1.5, question number 1.5. Then 1.5, question number 1.5. Two identical circular rods of same diameter, the diameter is same and same length, the length is same, diameter is equal to same, diameter is equal to same and length is also same, subject to same magnitude of axial force. Force acting is also same. One rod is made out of mild steel, one is made of mild steel and the modulus of elasticity is 206 gigapascal. Young's modulus of mild steel is equal to 206 gigapascal, 206 gigapascal, Then the other rod is made of cast iron having modulus of elasticity 100 gigapascal. Second rod is made of cast iron and Young's modulus is 100 gigapascal. Assume both the material to be homogeneous and isotropic and axial force causes same amount of uniform stress in both the rod. The stress developed are within the proportionality limit of the respective material. Which one of the following observation is correct? We have two rods of same diameter, same length, same force, but they are made of different material. One is made of mild steel of Young's modulus 206 gigapascal and other is made of cast iron with a Young's modulus 100 gigapascal. And options are both rods along the same. In option, elongation is given. We have elongation delta is equal to PL by AE. Where P is the load applied, it is same, L is same, A is same. In this case, in these two rods, load acting is same, length is same, area of cross section is same. So we can write deflection is inversely proportional to Young's modulus. So the material with shaft width made of material with a higher Young's modulus will deform less. The deformation of rod made with mild steel is less here because the Young's modulus of mild steel is higher, therefore the deformation of mild steel is less. So the option C, cast iron rod elongate more than the mild steel. Option C is correct. Since the Young's modulus of cast iron is less, the elongation of cast iron is more than the elongation of steel. Option C is the correct. Then 1.6, the figure below shows a steel rod of 25 mm square area of cross section. Here area of cross section is equal to 25 mm square. Area of cross section is 25 mm square. It is loaded on 4 points K, L, M, N Assume Young's modulus of steel. Young's modulus is equal to 200 gigapascal. Young's modulus is equal to 200 gigapascal. The total change in length of rod due to loading. We need to find out total length, total elongation of this rod. Now this is the rod given. We need to find out the total elongation. I am dividing this rod into 3. This is rod number 1, this is rod number 2, and this is rod number 3. Total elongation is equal to, total elongation is elongation of rod 1 or KL, elongation of KL plus elongation of second rod, that is LN, elongation of second rod plus elongation of third rod MN. So we can write P1, load acting on P1, L1, area of cross section is same, Young's modulus is same, plus P2, L2, area cross section and Young's modulus are same, P3, L3, AE. AE is constant, we can take it outside, it's a common factor, P1, L1 plus P2, L2 plus P3, L3. Now we need to find out P1, L1, P2, L2 and P3, L3. P1 is load acting at shaft number 1 or section 1, rod number 1. This is the rod number 1. To find out load acting at rod number 1, consider a section in rod number 1. Sum of forces towards left or right. Since this is in equilibrium, so sum of forces towards left and sum of forces towards right are same. If we are considering, I am considering sum of forces towards left, only one force is acting, that is 100, which is tensile. Since it is in equilibrium, the force acting on other end should be 100 tensile. So this is the shaft number 1 or KL. The P1 is equal to 100 Newton, which is in tensile, so it is positive. To get load acting at shaft rod number 2, consider section here, consider section 2 here, then sum of forces towards left hand or right hand side of section consider. I am considering left hand side of this section, sum of forces, 1 is 250 compressive, 100 is tensile, so higher force minus lower force, 250 minus 100 we get 250, and sign is sign of the force with a higher magnitude, 250 is compressive. So the total load acting on section 2 is 150, 250 minus 100, 150, and which is in compressive. This is shaft number 2, and load acting is 150, which is compressive, 150, compressive. Similarly, if I consider sum of forces towards right of the section, then 100 in compressive direction, 50 in tensile direction. 200 minus 50, 150 direction is compressive. So P2 is minus 150, and to find out P3, consider a section here, then sum of forces towards left or right. I am considering sum of forces towards right, and this is section 3. Here the force is 50 Newton. Since it is in equilibrium, here add equal and opposite force, 50 Newton is also tensile. So we get P3 is equal to 50 tensile. So we can write 1 by area of cross section. Area of cross section is 25. Area of cross section is 25. 25 into Young's modulus. Young's modulus is equal to 200 gigapascal. 200 gigapascal is equal to 1 by AE. A is equal to 25 mm square. E is 200 gigapascal. 200 into 10 raised to 3 megapascal into P1. P1 is equal to P1 is 100 Newton, 100 into L1. L1 is 500 plus P2. P2 is minus 150 into L2. L2 is length of bar 2 or length of section LM. LM is equal to 1700 minus 500 minus 400, 1700 minus 900, which is equal to 800. 800 into 800 plus P3. P3 is equal to 50. 50 into length. Length is 400. Solving this, we get is about minus 10 into 10 raised to 6 meter. That is equal to minus 10 micrometer. Minus 10 micrometer. Minus 10 micrometer. Minus 10 micrometer. Option B is the correct answer. Minus 10 micrometer. .7. A steel bar of 4 mm into 4 mm square cross section subjected to an axial compressive load 200 kilonewton. The length of bar is 2 meter and Young's modulus length of bar L is equal to 2 meter is equal to 2000 mm. Young's modulus is equal to 200 gigapascal, which is equal to 200 into 10 raised to 3 megapascal. And the load acting is P is equal to 200 kilonewton, 200 into 10 raised to 3 Newton. Length of bar is 2 meter and Young's modulus is 200 gigapascal. The contraction of the bar will be elongation or contraction delta B is equal to PL by AE, which is equal to P is equal to 200 into 10 raised to 3 into L. Length is equal to 2000 by A. Area of cross section 40 into 40. Then Young's modulus 200 into 200 into 10 raised to 3. Solving, we get 1.25 mm. Option A is the correct answer. Option A, 1.25 mm.